A sparse table is a preprocessing structure for a static array. After an O of n log n build, it answers range queries in O of 1 time. The classic examples are range minimum and range maximum query. Given indices L and R, return the smallest or largest value in that subarray. The same table layout handles both, only the combined step changes from min to max. The table stores the answer for every power of 2 length block starting at each index. To query a range, we combine 2 overlapping blocks whose lengths are the largest power of 2 that fits inside the interval. This works for other idempotent combines too, like greatest common divisor, but not for some, because overlapping elements would be counted twice. Sparse tables are static. If values change, rebuild the table or use a segment tree instead. A sparse table is structured as a two-dimensional grid. The base layer, where the row index j equals 0, stores windows of length 2 to the power of 0, which equals 1. This row is a direct copy of our input array, where each cell represents a single element. The next layer down is row index j equals 1. This row is allocated for windows of length 2 to the power of 1, which equals 2. Each cell in this layer tracks a block of 2 consecutive elements from the array. The next layer is row index j equals 2. The window length doubles again to 2 to the power of 2, which equals 4. Every cell in this row is designed to cover a block of 4 consecutive elements. This pattern continues for all higher powers of 2. Because the architecture only allocates rows for window sizes that are exact powers of 2, completely skipping sizes like 3, 5, or 6. The total height of the table is bounded strictly by log base 2 of n. This forms our complete data structure blueprint. To fill our table efficiently, we do not scan the raw array. Instead, we use dynamic programming. To calculate the minimum of a window of length 2, we combine the pre-calculated answers of 2 smaller windows of length 1 from the row directly above us. Let's calculate the value for row 1, column 0. This cell needs to store the minimum of a length 2 window starting at index 0. We pull the answers for the 2 halves from row 0 directly above us. The first half is at the same column, column 0, which holds a 4. The second half is 1 column over at column 1, which holds a 1. The minimum of 4 and 1 is 1, so we write 1 into st row 1, column 0. Moving to column 1, we repeat the process to fill st row 1, column 1. We look directly above at row 0, column 1, which gives us a 1. Then we check the next adjacent block over at column 2, which gives us a 5. The minimum of 1 and 5 is 1, which populates our cell. Moving forward once more to column 2. We look at the final pair of single blocks in row 0, 5 and 3. The minimum of 5 and 3 is 3, completing row 1. This identical lookup logic applies as we move down to row 2, which tracks windows of length 4. To fill our very first cell here, st row 2, column 0, we look at row 1 directly above us. We take the value at the same column, column 0, which is 1. Then, because our previous window size was 2, we leap over 2 columns to grab the next adjacent block at column 2, which is 3. The minimum of 1 and 3 is 1. By building row by row, from top to bottom, we fill the entire table using simple lookups in total O of n log n time. Now that our table is completely built, let's look at how it processes queries. Suppose we want to find the minimum value in our array from index 0 to index 3. The total length of this window is exactly 4 elements. Because the length of our query window is a perfect power of 2, we can find the answer instantly. We take log base 2 of our length, 4, which gives us a row index of j equals 2. This tells our code to look directly at row 2 of our table, which was built specifically to store blocks of size 4. Next, we need the column index. Since our query window begins at index 0 of the original array, we look at column I equals 0. Combining our row and column gives us the exact cell coordinates, st20. We look inside that single cell and find the value 1. Because the table already did all the work during construction, we don't have to loop through the array or compare any elements. We read a single cell and return the answer in constant O of 1 time. What happens if a query window length is not a perfect power of 2? Suppose we want to find the minimum from index 1 to index 5. The total length of this window is 5 elements. There is no single row in our table built for a window size of exactly 5. To solve this without looping, we find the largest power of 2 that can fit inside our target length of 5. By taking the floor log base 2 of 5, we get a row index of j equals 2. This tells us we can completely cover our range using pre-calculated blocks of size 4. We cover the length 5 range by dropping 2 overlapping blocks of size 4. The first block starts at our left boundary, index 1, and extends forward. The second block ends exactly at our right boundary, index 5, and extends backward. They overlap heavily in the middle, but together they ensure no element is left unexamined. Now we look up these two precise cells in row 2 of our table. st21 gives us the minimum of the first 4 elements, which is 1. st22 gives us the minimum of the last 4 elements, which is 2. Finally, we take the minimum of these two values. Because finding the minimum of a range is an idempotent operation, meaning looking at the middle elements twice does not change the result, this overlap is completely safe. No matter how massive or uneven a query window is, we can always cover it completely using exactly 2 overlapping blocks from our table. Because this requires just 2 cell lookups and a single comparison, every single range minimum query can be answered in absolute constant O of 1 time. Let n be the length of the input array. Building the sparse table is O of n log n, we fill about n times log n cells, each with a constant time lookup into the row below. Every range minimum query is O of 1, read 2 table cells and take 1 minimum. Space is O of n log n for the full 2-dimensional table. The array must stay static, there is no cheap point update like on a segment tree. Here is the pseudocode for the 2 routines from this tutorial, building the sparse table and answering a range minimum query. Build first allocates a k by north sparse table street. It copies the input into row 0, then fills each higher row j. Every cell combines 2 adjacent blocks from row j-1 using min. Range minimum picks the largest power of 2 block that fits inside the window, reads the cell aligned to the left boundary and the cell aligned to the right boundary, then returns the minimum of those 2 values.